Pythagorean theorem is the theorem almost everybody remembers from geometry class. It is the classic a squared plus b squared equal to c squared, where the square of the two legs of a right triangle is equal to the square of the hypotenuse. This is specifically for a right triangle. Later in this class, we will learn about the general Pythagorean theorem that applies to any triangle, but for right now, Pythagorean theorem is only for right triangles. Now, the reason that we want this is because the relationship of a squared plus b squared equal to c squared can be translated onto a coordinate grid when we start having our standard angles around the circle. Our trigonometric functions, and this is a chart that I would have the chart written down this way, and I am going to color code this one, and I would give you some time to color code because it is that important. X comma y is some point in a coordinate grid, and if we connect that point to the origin and then have what's called a reference angle going straight down, we can create a cute little triangle based on our angle. So for example, we have this distance x, which is the x coordinate of that coordinate point x comma y, and we have this y coordinate here. It's a distance to go up to the coordinate point. The triangle then has a radius r that's working as the hypotenuse of the triangle. Again, this is made from one of your angles on the screen. Yes? Should we be writing this down? I would write for sure at least the definitions and draw the picture. You don't need all the words up at the top. Okay. But we can define 6 different trigonometric functions from this triangle for the angle, reference angle theta. The sine function, written as sin of theta, and if you say sin theta, I will charge you a QuickBook. It is sine of theta, is defined to be the y value over the r value for that triangle, or for that coordinate point. The cosine function, which is spelled cos of theta, and if you say cos theta, you owe me a QuickBook, is x over the radius r. So it's your horizontal displacement over your radius. Tangent is the ratio, tan of theta, is the ratio of the vertical displacement and the horizontal displacement. So it's our coordinate point x and y. If you're thinking to yourself, okay, we have the coordinate point x and y, how did we get r? That's something I forgot to say in this little blurb up here. R is found using Pythagorean theorem, where the legs x and y can be squared, and it would be equal to the square of the hypotenuse, which is the radius. So we find the radius by square rooting both sides. Those are the 3 basic trigonometric functions. There are 3 more that are the reciprocal functions for these 3. Cosecant, which is CSC of theta, cosecant is the reciprocal or flipped fraction of sine, meaning it is defined to be the radius divided by y, making sure that y is not equal to 0 because you can't divide by 0. Secant is the reciprocal of cosine, so you flip over the cosine function to have r over x, again making sure x is not equal to 0 because you can't divide by 0. And then cotangent is the reciprocal of tangent, C-O-T, don't call it cot, that's so annoying. It's called cotangent, is the reciprocal of tangent, x over y, again, denominator can't be 0. These 6 definitions are the basis of what we're going to be doing all day long. It's very easy once you have the values of x, y, and r to literally just place them into these formulas where you need them. In this section, we'll be given problems that may ask something like this. It says, the terminal side of angle theta in standard position passes through the point 8, 15. Find the values of the 6 trigonometric functions of angle theta. To do this, we're going to first draw a picture so that we know where in the 4 coordinates this point, thus the angle, would lie. So if we draw ourselves like a quick little coordinate grid, the coordinate point 8, 15 would be over 8 and up 15. So it would be somewhere here in quadrant 1. That's a horrible line. Let me try that again. This would be the coordinate point 8, 15. It creates a triangle if you draw a little reference line straight down. Thus, we are finding all of the trig functions for this angle theta. We only need 3 pieces of information to do this. We need an x, we need a y, and we need an r. You already have 2 of these things. Based on the coordinate point 8, 15, what is x? 8. What is y? And how do we find r? How is r related to x and y? X squared plus y squared. So this is a moment where we would probably want to use a calculator. We're going to find the square root of 8 squared plus 15 squared. Bless you. If the number comes out to be a decimal, you're going to back up and leave it in radical form. This one doesn't. When you do 8 squared plus 15 squared, it's 289, and the square root of 289 is 17. Nice and easy. Otherwise, you do reduced fractions. Nope, what's that called? Simplified radical form, then reduce your fractions. To find the 6 trig functions, we just plug the x and the y and the r in where they should be. So if we're doing this, sine of theta should be y over r, the end. I've got one of them, 15 over 17. Cosine of theta would be x over r. Tangent of theta would be 15 over 8. We see how if they're labeled, we can just plug them in, yeah? And the reason I'm doing them like this, where sine, cosine, and tangent are like stacked like this, is because if you remember which function is the reciprocal of which, all you have to do is flip these fractions over. The reciprocal of sine is cosecant. So cosecant of theta is just 17 over 15. Flip that fraction. Secant of theta is just 17 over 8. Flip that fraction. And cotangent of theta is equal to 8 over 15. Flip that fraction. Boom, there's all 6. In example 2, it's the same exact question. It says the terminal side of angle theta in standard position passes through the point -3, -4. We're going to find the values of the 6 trig functions of angle theta. Again, it's very helpful to always see what quadrant this would be in. For -3, -4, that means we're going to the left 3 and then down 4, so -3, -4 is somewhere here. So my angle, boop, boop, is this larger than 180 degrees, smaller than 270 degree angle. That's theta. But if we just draw a little reference line to create a triangle, we still have a triangle down there to do trig with. Again, we only need x and y and r to find all 6 trig functions. What is x? -3. What is y? -4. And the relationship between them is Pythagorean theorem. So we can find r by doing the square root of -3 squared plus -4 squared. If you know your Pythagorean triples, though, what is r? Do we not know our Pythagorean triples? 5. It's 5. So -3 squared is 9, -4 squared is 16. 16 plus 9 is 25, and the square root of 25 is 5. 3, 4, 5 is a Pythagorean triple. Radius is always positive, by the way, because it's a distance. Okay, let's put together our sine, cosine, tangent, and its reciprocals. So sine of theta is going to be y over r. Cosine of theta is going to be x over r. And tangent of theta is going to be y over x. When I put y over x, that's -4 over -3. Do I need both negatives? No, because negative divided by negative would be positive. So we can rewrite this as 4/3. Again, I'm writing them in this way so that we can just flip these for their reciprocals. Cosecant of theta is -5 over 4. Secant of theta is -5 over 3. And cotangent of theta is +3 over 4. And I just realized I didn't take roll yet. Our third and final example today is the same question, except that I didn't just give you the coordinate point. We're asked to find the 6 trigonometric functions of angle theta and standard position if the terminal side of theta is defined by an equation x plus 2y equal to 0, with the caveat that x has to be greater than or equal to 0. We're going to rationalize any denominators that we find. So we still want a coordinate point so that we can see which quadrant it lies in and what our x and y values are. So what we're going to do is we're going to take the equation x plus 2y equal to 0, and we're going to solve it for one of the variables. It's easier to solve for x, so that's what I'm going to do. This means that x has to be equal to negative 2y. We need to find two numbers that satisfy x and y in this example. So for example, don't write this down, just listen. If x was equal to 1, what would y have to be so that this ends up also being 1? Negative 1/2, because negative 2 times negative 1/2 is 1. You could use those numbers. I don't want to use a fraction though. So I would probably try a different number. What's a number I could try? 4? What about 2? If x is 2, what would I have to plug in for y so that both sides were equal? Negative 1. Now that's not too bad to work with, meaning our coordinate point is 2, negative 1. We make sure we look again. It does say that x has to be greater than 0. Is our x value greater than 0? Is it? Yeah, our x value is greater than 0. Our y value is less, but it doesn't say anything about that. So if we look at our coordinate point, 2, negative 1 would be somewhere like this. This is in quadrant 4. For those of you who know All-Star Trig class or all students take calculus, that means cosine will be the only positive values. If you don't know what I'm talking about, just ignore. We'll get there eventually. This means that x is 2, y is negative 1, and we have enough information to solve for r. We would find r by doing 2 squared plus negative 1 squared. 2 squared is 4, negative 1 squared is 1, so inside there we have 4 plus 1, which means we have the square root of 5. Can we take the square root of 5 and get a whole number? No, so we're going to leave it as square root 5. So if we start to set up our problems, and I'm going to show a couple steps of work here on purpose to help another problem get easier. If we're finding sine of theta, we defined sine of theta earlier to be y over r. Well, Spidey senses should be going off. You are not allowed to leave radicals in the denominator. We need to rationalize our denominator. So what we're going to do to rationalize a denominator, you don't need to write this down as long as you understand what it means. We can rationalize a denominator by multiplying by the square root that's in the denominator as a scalar of square root of that number over square root of that number. What it does is it allows me to write something like this. If I'm rationalizing 1 over square root 5, multiplying by square root 5 over square root 5 gives me 1 times square root of 5, which is square root of 5. And square root of 5 times square root of 5, which is square root of 25, which is 5. This is the same number as this in rationalized denominator form. In other words, take this radical, move it to the top, rewrite the number with no radical. In which case, if we're writing this number, we would move the radical to the top, rewrite the denominator without the radical. If we were writing cosine of theta is x over r, and so same thing, we need to rationalize our denominator. Mathematically, we're multiplying by a scalar, but really what you can tell yourself is move the radical to the top, rewrite the number underneath the radical. Tangent of theta is y over x, which is negative 1 over 2. That's nice. We don't need to rationalize anything there. Now, the reason I made you show a couple steps of work in the first two, even if you could rationalize in your head anyways, is because if we're writing cosecant, cosecant is the reciprocal of sine. But if you do the reciprocal of this number, you would put a radical back in the denominator and it's really annoying. Why don't we just do the reciprocal of this number? If you flip this number over, what do you get? Over 1, which we don't need to write. So I didn't have to rationalize the denominator again because I was already moving it out of the denominator. If I'm finding secant of theta, again, rationalizing this one is a lot of work. So why don't we just flip this bad boy over? This ends up being square root of 5 over 2. If we flip over negative 1/2, we end up with negative 2. And again, for those of you who know what quadrant is positive, notice that cosine and its reciprocal are the only positive values here because we were in quadrant 4. Again, these two boxes, you might not need to write them down. Maybe the rationalizing denominators is new for you, so you might want it, or at least the little trick of move and leave the number. But I did want to make sure a caution was, why is this number negative 5 floating around somewhere? Get rid of that. Make sure this caution is written for you on your notes. One of the most common errors involving calculators in trigonometry is not using them in the correct mode. When you reset a calculator, it resets into radians. And if we are using degrees, which we will be for the first 2 or 3 chapters, I think 2 chapters, we need to make sure that in our calculator, we are always changing this to degree mode. This should be something that we remember because if I'm making you write down the degree symbol, you're having to go out of your way to tell me degrees. So on your calculator, you need to go out of your way to tell me degrees. You don't have to put a degree symbol if it's in degree mode. Does that make sense?